Well, ciao. I'm going to try and talk about a whole new subject, I hope, for this field. And I'd like to first thank Bill Collis for arranging the meeting and inviting us here. And two, I'd like to apologize because when I put the abstracts in, the figures didn't come out. So I'm going to spend a couple of minutes reviewing the pictures from the three papers so you can get a better idea of how it all fits together. This is an important subject, I think, because we know that active lattice-assisted nuclear reaction components produce excess heat, de novo helium, low-level emissions, and as I've shown over the last 3 years, anti-Stokes spectra that are unique to the active state. And here we have something new, which is they also produce RF radio frequency emissions at the deuterium line. And I'll briefly review that. So since the pictures didn't make it, I'd like to give you a quick overview. What we're looking at here is frequency. And this is approximately 30 kilohertz. And we're looking in the region of 327 megahertz. So what you're looking at, and I'll show you how we collect the data and image it, is we have a nanor component. A nanor is a preloaded, dry zirconium oxide, palladium, highly deuterated material that has two electric wires coming in. It's a two-terminal component. And with no voltage across it, we see nothing. And when we put on 1 volt and raise a little higher, we get a very high Q signal. As I'll show you, and to show you how high Q it is, although you can't buy a radio transmitter at these frequencies, these are protected frequencies, you can buy it in China. And so I picked one up here, and so here's the output of a typical radio, and here is the output of the cold fusion device. So the Q is incredibly high compared to standard radios, and we'll talk about why that is in a bit. It turns out if you take the component, and so far we've gotten these emissions both from aqueous nickel systems with ordinary water, and I think there that the deuterium is the active material, I'll tell you why shortly, and with these preloaded dry components, what we see is when we put it in a Fabry-Perot box at a half wavelength, we get a maser. And here, we're at 327 megahertz. Let me explain this a little bit. On the top is an instantaneous measurement of the radiation that's coming in. So we see galactic inputs, and we'll talk about that. And here is the maser. And down below, it's called a waterfall. And so time goes in this direction. And here we turn on the cold fusion device, and there's usually a little bit of drift, and finally it reaches equilibrium. We'll talk about that. And it's an incredibly high peak. What you're looking at here are galactic outputs, and usually I'll show you how we filter them. It's just what we talked about, how to read it. The other thing, we have 2 more papers coming out on this on Thursday and Friday, and what I'll show is when we raise the voltage across the device, I showed you 1 and 2 volts. When we go to about 24 volts, all of a sudden sidebands appear. And they appear at locations that in fact tell us where the active site is in palladium. And finally, we see pulse, and I'll show you that here. For example, here, we're driving it at 2 volts. And here, when we go to 15, all of a sudden, these sidebands appear around it. And these sidebands are at positions where when we consider resonance broadening, as we'll talk about tomorrow, we are seeing atomic deuterium. Free radical deuterium is the precursor to helium-4, and these sidebands will show us that, in fact, it's occurring in a face-centered cubic vacancy within the palladium. We also, as I'll point out on Friday, we see rarely pulsatile bands. And I've been at my wits' ends asking for 4 months what the pulsatile bands herald. And I think yesterday's paper by another scientist, as I'll explain later, may explain what's going on, where when we see the amplitudes change, the Coulomb barrier falls. So the first question is, why did I even look here? Initially, I looked at the hydrogen band, which is at 1.4 gigahertz, and didn't see much. Then I went down to the deuterium band at 327 and saw quite a bit. So the reason I looked is, in fact, hydrogen provides the fuel. When we look into the galaxy, we see these lines are incredibly important. In fact, they're in a protected region of the electromagnetic spectrum. And therefore, we have to be very careful. If you follow me and do experiments in here, you need a double Faraday cage. And we'll talk about that. Now, what we're seeing is a result of hyperfine splitting. And when the Pioneer 10 and 11 went out, we sent out to the universe, hopefully we thought somebody might see it, this to indicate the hyperfine lines. And what they are is an interaction between the deuteron electron and the nucleus, and it creates a very high Q, very narrow band emission. And the reason basically that it's narrow band is there's no electric dipole moment. So electromagnetic emission is forbidden. In space, the half-time is 100,000 years, and that's why these lines are so thin. What you see here is for hydrogen at 1.4 gigahertz, and when you look at the deuterium line, as I say, it's at 327. One of the problems is to calibrate your system and to eliminate the background. And most of the background is caused by galactic origins. And as you know, when we look at our galaxy, the biggest emitter turns out to be in the center. And this is quite important. This came from the history of radio astronomy. And basically, this is at MIT, this one's at New Jersey, these other ones are at MIT. A lot of people have spent much time over the years, go back and read the literature of how people have used array dipoles to pick up these emissions from space. And has it been helpful? Incredibly helpful. Here we see the image, what we see optically, and here's what we see with the radio frequencies. We see mass that you cannot pick up optically. And so, for example, here with ordinary light, all we see is two galaxies interacting, but when we look at the hydrogen line, we end up seeing much more. We see the interactions. We see things that are normally hidden with ordinary light. Okay. What we're looking at, these are the significant radio astronomy frequencies that are all in a protected region now, and we're looking at 327. And it turns out that lattice-assisted nuclear reactions emit slightly lower. I don't know why. I'll show you there's a drift. I don't know why. Maybe, I hope somebody here can answer these questions. So here's how we do it. We have had active reproducible systems in cold fusion, both in aqueous that we showed in an open demonstration at ICCF10 for several days, in the nanomaterials that we showed at the IAP class at MIT in 2012, the Series 6 nanors. And from these, we developed the anti-Stokes technologies, and now we're seeing the deuterium line spectroscopy that I'll show you. The other system we use in the aqueous system, this was the, we call it the MOAC, the mother of all cathodes, because it has half a mile of nickel wire, and here it's unfilled. And when it is filled, it turned out that at Lincoln Lab, they did a series of measurements, and they found that when they got excess heat, the deuterium fell. There was a 43 loss of deuterium. Why didn't they report it? They were looking for hydrinos, and they found none. We have used the same system and have discovered quite a bit. Here's one of the outputs, for example. Here's our input. I do ohmic controls on everything. Whenever we have a lattice-assisted nuclear device, whether it's dry or aqueous, we'll put a resistor next to it at the same location so that we can calibrate the calorimeter explicitly. So here, for example, is the ohmic control. Here is the heat coming out almost nil. Here is the MOAC, and we put in even less electricity and more heat comes out. And this came from ICCF21 when I showed that these devices, real cold fusion components, have two states when they're driven. And a lot of people waste their time because they're in the state that's off. In fact, only one of the two states is active. And here we can see the difference. In the active state, we get excess heat, and then we drove it to where it's inactive, and we just get hydrogen evolution and much less heat coming out. So if you want to get an active system, you see it here. And what we'll show you is that when we electrically drive the dry preloaded components and the wet MOAC, what we are doing is driving in the active region. Okay, and these are the dry materials. We've been showing them for several years. We did the open demo at MIT. This is one of the outputs where, again, OMA control, always using OMA control. Here is the input, here is the output. We put in less to the nanoroid dry type component, we get more heat out. And we can see the same for heat flux. We can see the same for full bore calorimetry, as we see here, where we get we do one other thing, of course, which is we do the time integral. You should always do a time integral because you can pick up phase change, you can pick up errors. So here, for example, we see for the OMA control, we get out what we put in, and here's the energies. And yet with the cold fusion device, we put in less, we get more heat out, and in fact, the energy ramps separate. And that's what we use to confirm we're really getting excess energy and excess power out. This is just another delta T. What we try to do is normalize the delta T to the input power, and then we get a flat line no matter what input it is. Flat line, relatively flat line. And we can see there's quite a significant gain here. Typically, what we were seeing was a gain of 1,200%. And from cycle to cycle, it's reproducible. OMA control, OMA control, OMA control, OMA control, and here's the cold fusion device over time. This is the impact of magnetic fields. We don't have to do it. We use these devices. We got to image them by using CR39. Peter and I showed, in fact, that if we up the voltage, we get an electrical avalanche. And what happens is once we go and get the electrical avalanche, we don't get any excess heat anymore. And what happens is, so for example, here, I spent a lot of time trying, here's the OMA control, and here's the cold fusion device, lots of excess heat, and as we up the voltage, we finally turn it into a resistor. And if you can get a component where you're getting excess heat and then drive it to inactivity, it's yet a further calibration and control that you really did have an active system. And the other thing is, once we have active systems, we discovered about 3 or 4 years ago that we get anti-Stokes lines, and this is a picture of it where here, for example, is off, no electric drive. Here is in the avalanche. We do not see the anti-Stokes line, so we're not getting excess heat out. When we adjust it correctly, that we get a massive amount of excess heat out, there is a big anti-Stokes line here. And we have a series of papers in CMNS proceedings that you can go through to see how to do this. And by the way, if anybody wants to build a Raman spectrophotometer, you can 3D print it out. Just call me, I'll send you the STL. And this just shows that when you do the Raman spectroscopy, you can also pick up the optical phonons that Peter Hagelstein predicted when you're in the excess heat state. Okay, now let's get to this, the methods. So we take our component and we put it in a Fabry-Perot structure, although some of the ones I'll show you were before we got the Fabry-Perot box. We need an antenna, we need a transmission line, you've got to have an amplifier here, and finally you put it into a software-defined radio. These are available now for under $200. Send it to your computed system. And basically, the key things you have to do here is adjust the standing wave ratios. You've got to make sure that your coax isn't lossy. I'll briefly show you how to do it. And you've got to add your low noise amplifier to pull this off. So we start with Maxwell's equations, but I pulled all those slides so we don't have to do it. But you do have to do the right antenna. And there's several types that we use. We've used a Yagi. We use what's called the normal mode helix, called the duck antenna named by Carolyn Kennedy, and the Secret Service picked it up, and since then everybody uses that. And this is a tiny antenna that I'll show you that we put inside the Fabry-Perot box, which itself is within a Faraday cage, because we don't want any emissions of this into the environment, and we pick up a humongous signal. The problems we have that if you don't take care of, you won't see it. Radio frequency is terrific. You can do radio astronomy in your home. You can do it because the RF signals get right through the atmosphere. They easily go through things that other frequencies will not. And so there's a terrific window there. But the biggest problem is transmission lines. And it turns out that if you're a radio amateur like I am and you take your RG8U to connect it up, the losses are incredible. So we had to buy military-grade material, and we end up coming down by quite a bit. We decrease the attenuation by 10 to the 5th. If you do it, we'll give you more tips on how to handle that. So here's the experimental measurement. If you end up doing this, it's very like ultracalorimetry. What you're looking at is a change of temperature on the antenna, and the equations are actually quite similar to what we use in calorimetry, and the unit that they use is a Jansky. Where'd it go? Okay. The thing that's nice about this is the longer you measure, the less noise you have. The signal-to-noise ratio improves quite a bit. Here's the equation. And unlike other kinds of measurements, you can use time to improve your signal, and that's what we do. And we'll come more to that later. The best way to begin this, if you're interested, you've got to do controls. And what's most important is you've got a contaminating emitter in your background from our galaxy right at the center. And there's the emission coming out. And every day you have to check. In the beginning when we did this, I made sure that the Earth was blocking the center of the galaxy, and it's the only time in my life I've ever looked at the zodiac. But here you have to do it because what you want is the Earth to block it. Eventually it wasn't a problem, as I'll show you, because what we did was use a Fabry-Perot box and Faraday cages to shield everything out. But sometimes you want to let them in because that'll let you calibrate. So example, Peter Hagelstein suggested that I separate out some of these lines, and what we did, we found out these are from our galaxies, these are other galaxies. And it really is terrific. In fact, if you do Doppler shift in this, you can see back in time. And it's just incredible to me that this is just so new and incredible. These are galactic. The military does masers as well, and this is obviously a military maser here because galaxies don't do that. They don't turn off and on at that frequency. So the most important thing is grounding. And here I'll show you what you want to do. We put an 8-foot copper pipe into the ground with ribbon cable going down. It was really important, just as it turns out grounding is the most important thing you do here. So this is without the grounding. Inside the Fabry-Perot, we're still getting contamination from the galaxy. But if you do it right and ground it, you'll get a free signal, and you'll really be able to get data from this. Okay. Rule 1, all objects are antenna, and there is no other rule. So you've got to ground it. So let's show you the results. These are first for the dry, preloaded nanotype components. And I showed you this before. We got a beautiful output. High Q, we'll talk about that in a second. Here's another one. These are 2 different nanors. Series 7, we did the same as Series 6. These are not quite electrically loaded, but they're not pressure loaded. Pressure loaded does not work well. It comes right out within a month. So this is 7.4, 7.5. These are 2 different nanors, and they're both putting out D lines, deuterium line emissions. And when we put it in the Fabry-Perot box, here I'll show you what it is. Here's the nanor over here with 2 wires coming in. Here's the ducky antenna. And the resonant wavelength, this is half a wavelength, is just over 36 inches. And when we do that, we get an incredible maser output. And here again, what we see the evidence of the maser emission, both here instantaneously, and here is a function of time. Actually, time goes backwards. I guess I got that arrow backwards. It's called a waterfall. It falls down, but therefore actually time goes up, and we keep a time log on the side. And here you can see I put on the applied electric field across the preloaded component, turns on as a maser, drifts slightly, and finally they equilibrate. And this is before, only 4 minutes left? Yeah. I gotta move fast. All right, how do we know that it's a maser? We know it's a maser because it's linked to the excitation. We know because the Q is almost 10 to the 7th. We know that these emissions are forbidden on Earth. You're all familiar with photoelectric emission. There you have spontaneous de-excitation as well as the fact with a laser where it's stimulated emission, but we don't have that in the microwave region. To make it fast, this is the equation, and I'm going to have to jump ahead here. The other issue is, in addition to these lines, there's a wider output, and I'll just show you quickly if I can get to it. I probably won't. This is the Q factor. Q is a non-dimensional number. It tells you basically the ratio of the half power points of the width to the frequency. And there's two definitions. We don't have time to go over it. Larry Forsley had suggested when I first presented this at the MIT colloquium that we should look at what the broadening tells us. I won't have time to tell you, except I can show it here quickly. Doppler broadening is not seen. These things are not moving very much before they emit. We are getting resonance broadening, and I'll talk about that tomorrow. This is important. This is proof that it is a maser reaction. Masers, if you put a magnet in the emission side, you get a splitting, as we see here. But in fact, when we move the magnet to the side, it disappears. This stays as a singlet. This is the wideband emission. Hold on. Let's jump to the conclusions.
You can take a couple of minutes, but it'll count against your question time.
Only fair. The important points. Electrically driven active cold fusion devices emit at 327.7. This is the deuterium line, slightly lower. They, ordinary water systems with nickel also emit. We couldn't get the big device into the Fabry-Perot structure. We'll need some money to make a bigger one. So this is the first solid-state cold fusion maser that has been made. It has a positive Zeeman effect proving it's a maser. And we've done all kinds of ohmic controls. They've never shown anything. So it's clearly and uniquely a result of active cold fusion. The Q is incredibly high, though we didn't get to talk very much about the definition. It's 9 million, and as I showed you, compared to ordinary radio devices, we're dealing with 1,000th of the width to 10 millionths of the width. The most important things here, if we raise the voltage, we see sidebands, and I'll show you tomorrow. This tells us that the active free radical deuterium, that is the precursor to making helium-4, is sitting in a face-centered cubic vacancy within palladium. If we turn off the electrical activation, there's a slow fall off of these bands that takes several minutes. It does not happen instantaneously. And there's an initial sideband shift. The most important thing about this talk, this is absolute confirmation that free radical deuterium is the fuel of cold fusion. It is the precursor to helium-4, and as I'll show you tomorrow, it gives us information on the location, which is the vacancy. And these are some references.
Thanks, Mitchell.
Okay, thank you.
Is there any chance that you would be able to detect an excited product from the Leonard reaction?
If it's excited and emitting radio frequency, yes. Tell me where to look.
I mean, have you looked for helium-4, for example?
No. No, I'm a newbie at this. I just picked the two frequencies that I thought we might see something. That's a great idea.
When you have a reactor that goes into avalanche, you mentioned that you are seeing some avalanche currents. What exactly is the voltage and what kind of currents are you running in order to induce that avalanche?
Okay, basically, we see a increase in electrical currents from, let's say, 10 microamperes to milliamperes. And the increase in voltage, the voltage across will fall. Typically, when we run these dry preloaded components, we are putting on something, the early ones, between 600 and 1200 volts. And after avalanche, we come down to 10 volts, 20 volts. It's in the papers where we showed the signatures and the voltages and currents are listed.
It sounds like the conductivity of the nano increases when the avalanche effect occurs, right?
Yeah.
But how much does that compare to the material before you put the deuterium in?
How much is what?
How much does that compare in terms of conductivity against the material before you put the deuterium inside?
The conductivity goes way up, way up. I'll give you the paper on that.
Mitch, how do you think the pumping occurs?
Which pumping?
The pumping of your state that you're radiating from, the RF state.
I think we're getting the pumping from the electric input. We're driving these continuously with an applied electric field, and usually from a Norton equivalent.
Yes, you mentioned that the sidebands prove that these radicals are inside the lattice. So
It appears to, but tomorrow we'll hear
okay.
some criticism for it.
Okay, so because I think that's probably important to know whether it's fuel or whether it's somewhere at the surface in the electrolyte generated. So yeah, this is what I wanted to ask, that how do we know for sure that this is the fuel and not electrochemical radical?
I don't have any aqueous material.
Oh, I see. So it cannot be electrochemical radical because this is a dry experiment.
Mitch, can you say something about timing? I'm way the hell in the back. I'm aware of experiments in which an RF signature is seen as a precursor to heat production. What is the timing in your case?
Synchronous with the heat.
Say again?
In fact, when we go past the optimal operating point, the output falls off.
So-
when we go into avalanche, it falls off.
So as far as you can resolve, the two things occur simultaneously.
Correct.
When we were with Piantelli, he said that if we don't build his reactor exactly the length he specifies, it will never work. And he then went on to describe that once when he was turning on his reactor through the glass pass-through, he ended up with a huge burn on his arm.